Hi everyone, and thank you for joining us this afternoon or this morning, wherever you're dialing in from, for our next in our instalment of Inform webinars. This afternoon's webinar is in collaboration with the team at Tinius Olsen. First off, my name's Chelsea, and I'll be hosting today's webinar on behalf of the team at the Institute of Materials, Minerals and Mining. So before we begin today, I'd just like to take the opportunity to tell you a little bit more about who we are and go through some guidelines on webinar etiquette. So the Inform webinar series has been designed to give you the opportunity to learn about the latest advances in technology from those working in research and manufacturing. And we're very pleased to be able to showcase today composites usage and development within exoskeleton technology. So there will be the opportunity at the end of the webinar for a Q&A session. If you do have any questions throughout the webinar, please use the Q&A button at the bottom of your screen to enter those questions, and we'll get through as many as we can at the end of the session. So without further delay, I'd be delighted to introduce you to Sean Bird, who's the technical manager at Tinius Olsen. So fire away, Sean, thank you.
Thank you for that, Chelsea, and welcome everybody, wherever you are. It's an honor to be here today, and really excited to have this collaboration with my colleague and good friend, Dr. Matthew Dickinson. We've been working together for well over a year, and this is an exciting platform, and we look forward to getting the feedback. I'm quite sure with the information you'll receive from Dr. Dickinson, you'll be enthralled and excited by the time you leave this webinar. So without further ado, I'd like to introduce you to my friend and my colleague, Dr. Matthew Dickinson.
Thank you, Sean. Firstly, let me just say welcome everyone, wherever you are in the world. This is a really exciting time for me and my team and what's been going on. So without further ado, let me share my screen and let's take a look at some of the work that we've been doing. So to give you a little bit of a background as to who I am a senior lecturer at the University of Central Lancashire, and I specialise in concept design, and I do a lot of simulation work. So I look at dynamics, and I look at FEA analysis, and this technology, this project has slungshot us into a whole new area, which, to be absolutely honest, we originally did not truly appreciate where this was going to go. But what I'm going to talk to you about today is technologies for an improved quality of life. But let me move on. So just to give you a bit of a content as to what we're going to talk about, I want to introduce you to the challenges and the big thing, what it is not. So when we hit it, I want to introduce you to what the idea is and where that comes from. We're going to discuss how this has been talked about to tackle these solutions, tackle these problems, and how we look for solutions, technology, moving into the exoskeleton project, and then moving to the phase, and then a little finish off by the collaborations team. So, introduction to the challenges, what it is not. This is something that I was introduced at a thing called healthy aging. And I won't lie, at first, when I first thought this, I kind of thought, what is this? I'd never heard of it. And it has a huge implication. It can affect the population. It will affect the population on a grander scale. And what I mean by what it is not, I'm probably going to disappoint some people in the audience, but we are not building Iron Man. It's the most common thing that colleagues across in different areas of development of exoskeletons get asked. Are you building Iron Man? No, sadly, we are not. So implications. Now, when you consider the world is getting older, and it is predicted by 2050 that, as you can see in the image, that 30% or more in the larger, deeper blue states will be more of 60 years or older in that particular time. And the big question is the economy. So, does this affect the economy? Yes, it does. In terms of workforce, it is now at present estimated that 1 million people aged 50 or above have had to leave the labour market due to health conditions. To really address this and to try to support some of our workers on the shop floor or in all different states could meet a lot of the big aspects of it will allow them to live a more productive, more healthier life. And also, it could actually introduce a solution to tackling some of the so-called loss of skills between particular ages. Healthcare. And at present, estimated that men at the age of 65 can or could live another 19 years. But interestingly, only 10% of those will will be in good health. When you consider women, they can roughly expect around 21 more years of life, but again, only 11% of those will be in good health. And granted, this may not be completely across the board to key areas. This could be other influencing factors that we're talking about, but part of these will be about that stress on the body as we're leaving the job market. And then finally, social. So these are all implications that will have an effect on everyone's population, economy, sorry. So the essential quality of life for individuals, it's estimated that in healthcare, they've been presently spending 3.3% for social care. And it's been estimated over the next 15 years, this will increase by 3.9%. This is huge. This is an alarming amount of funding for caring and so forth. I mean, don't get me wrong. What we're about to talk to you about today is not just about this. It has a bigger implication. But let's just think about how we solve these particular problems, tackling them. One way could be services. What about hospitals, support systems? Could we put in more hospitals? This relies on funding. This relies on a lot more aspects to it. This is us more trying to find a solution at the back end of when this has happened. So what about prevention? Keeping people well informed, keeping people active, introducing almost exercise regimes that's recommended. Now, especially here in the UK, this is something that is taught to us in schools, but the key aspect about this is, do people do it? This is a huge element of, do people actually really address these as they're moving forward? What about transport? Electric cars, scooters, making this technology more accessible for people to be able to get around. Because don't forget, in some of the key points above, I was referring to if these were healthy people who become injured. But what about those who are born who don't have the ability to be able to clearly get around? Nutrition, we could educate people about the diet, making sure they eat the right thing. And a bit more in this side, but again, maintaining that good health, keeping people well educated, putting in important aspects right through to almost junior school, really trying to educate children right before they become adults to ensure that they live the most healthiest life that they can. Community and social enterprises, these a strong suggestion of results has been that communities and social enterprises within even communities, housing communities, has proven to allow people to get out and to interface. Because one other aspect that I've not really noted here is that depression, loneliness can have a huge effect. But this is about our approach to one of these solutions: technology, software, and hardware. This is where what I'm going to center on today. This is what we're really going to be looking at. And this is where our project has gone to crazy directions, and I'm so excited to introduce all this to you all. Exoskeletons. To give you all a bit of an insight to the exoskeleton, when I first started doing this type of work, I was surprised. Originally formulated by Niklas Jagen actually in the very late 1800s. He proposed, I mean, it lasts to say, but he proposed a large actuator system, which was hydraulically powered, huge, monstrous thing. But the point of this is this is what was the very first forms. As you can see in my timeline here, not much really happens. We hit to the 1970s with, just realized an image has vanished, apologies, with the GE Handyman, where they were the first motorized and actuated exoskeleton system. And then as the electric motor miniaturizes, gets smaller, materials become better accessible, more pliable for different applications. You can see this huge explosion of where exoskeletons really start to hit in different areas. However, last year, one research group in Massachusetts proposed a different type of exoskeleton, which was looking at controlling the flexibility of the human body. Less of huge robot that drives the body and more of key joints of the body, and really examining that further. This, as you can see with some of the former ones, they were looking at this, but this was specifically designed around the spine. And this got a lot of people thinking, including us. We started to think about the same thing. So this is where our first real steps start to emerge. So we did the same thing. You're gonna have to forgive me for the name. We played around with silly names, and we decided to make our first one. We call it the Exo Move. The simple idea was, could you have single action sitting up? Some call it lying to sitting. So we took the human body, and we started to examine around the human body, and we thought, right, okay, we have key points. These key points is what in the Ross exoskeleton, which we'd just seen, which was designed around the spine, they were looking at something similar. They were looking at them key points of where our body is actuated. So this got us really thinking even more. So what we realized is, with these key points, what if we attach marker points to it? And we target these key points for motion. Again, what we're actually considering at this point is lying to a sitting position. Basically, think of it as a wearable recliner. I know it sounds crazy, but a wearable recliner just gives you the idea of the motion that we're essentially looking for. So we isolate that out. We know from that point then, we've now got groupings of areas. We're now trying to complement where that body's going to. And at this point, please do keep in mind, what we're doing at this point is we're just seeing, can we do it? Can we actually do what we're claiming to be able to do? Well, what we're hoping we can do, I should say. So then we move forwards. Now, I should point out, this got into lots of discussions with a colleague from work. We were discussing about the material that this was going to be made from. So we originally proposed, why don't we cut this? Why don't we take a billet and take sections of this skeletal structure? And one thing that's always been important to us is about the accessibility. It's about that everybody has access to this technology. It's great if you can offer technology to the rich and the wealthy, but what if this is a low income company or a low income family who need this to allow for a healthier living? So what we realized is cutting something from a metal was crazy. It was never going to happen. So what we did is we got into a large discussion about, well, in fact, I'll be honest, I sat in my office and sulked and thought, okay, how can I do this? I glanced over at my printer and I thought, what if I could print it? Everybody has a printer. Polylactic acid is the biggest printing material out there, completely out there. So this was the first provision. So we thought, right, let's make it, and let's just throw his feet in there and see what happens. The connector, which you can see on the lower left, this connector, the reason that we've got this is we have, as you can see, we have linear actuators attached. The problem is when the linear actuator moves in its specific linearized motion, if we were to attach this directly to the spinal section, there's a strong possibility that that linear actuator would push into the muscle unless assisted technology and more torture technology. So we knew that we needed something that would convert that linearized motion to a moment which would act around the actual spinal sections. This material, we decided to use the PET carbon. We've done some provisional tests and we pulled data sheets to give us an idea of the operation for it. It's a very green approach, as we'd originally thought. And what we also wanted to do as well is we wanted to replicate the spine. Now, there's lots of things in this, and I'm trying not to get too carried away, but we wanted to also allow that spine to move, to flex. Now, I think the next image will allow you to see this a bit better, but I'll show you this just for the moment. What we wanted to do is have a nitrile cable that ran through the middle, because again, what we're looking at is the lying to sitting motion. Could this material support the human body? In fact, more particular, we were more focused around children, if I'm honest. This is a particular point that me and my team firmly believe that this is a small area that has had very little development, and we're quite keen to focus this around the supporting of children. So now this is a nicer image of it. As you can see there, the black strips that run through the center, this is the nitrile. And the idea is we're essentially trying to recreate that sitting motion. So what we did is we focused on just children. We wanted to just look at children. And we found a few examples of where people were taking a look at muscle actuation and looking at muscle, what was coming out of groups of children aged between 10 and 13, if I remember rightly. And as you can see there, these are the particular averages that were extracted from these groupings. When it came to the lat area, we had to try and take the 90th percentile and try and fill in that blank. So it became a little bit awkward for us in that respect. But we built an overall picture of the types of forces that these muscles do exert. Now, I don't know who is involved in biomechanics, but you'll know that that level of muscle actuation is probably normal. But from when I first saw this, I was shocked. I'd never realized that this is what the typical muscle output could give. It was phenomenally interesting. So what we did is we extracted we chose to use two Actronics linear actuators. These were particular extensions. These would allow to support the body as it's moving through. And we thought that then we could at least support the lats and the trap area. So this is about that sitting motion. But before we could even start contemplate what we were doing, what we wanted to do is to break the human body down. Sounds crazy to say, but we wanted to break that human body down into sections. We wanted to consider component by component, and we wanted to consider the head, then the, as some would know it, the trunk, or the upper and lower core, whichever way you want to see it. So what we did is we went back to mechanics of the simple motion, the lever system considered on the head. Now, again, this was for us to understand, could this material do its job? Could it withstand something as active as the human head? Again, for anybody who's familiar with the force output on this, we simply take the resistance force, as you can see on the diagram, and we can take the force which is being actuated for that. And with that, what we're attempting to do is to assist this motion so that the human body wouldn't have to have that same level of force to output. And in that process, what we're then doing is considering the mechanics of the material when the head moves into place. So the modeling work. Obviously, we had a 3D model. At this point, we actually had a prototype. I mean, this is just two of us at the time. We're slowly trotting along with the project. And what we did is we fed this into an FEA system. Now, given the failure, given the displacement, the stress, and this was the rationale of the resistance force that we tested against. So what we did is we simulated the head acting actually on the let's call this the neck exoskeleton, when really this is just a section of that component. And then what we did is we looked at the interface actually on the connecting joint as well. What we were happy to see from provisional looks, from looking at what data sheets had given us, we were inside of a remit of operation. It was not going to fail. Again, it was an indicator. We can't solidly conclude that it would not fail unless we had some validation. And we were extremely keen to actually be able to get to this validation. So, as ever, like any good engineer out there, that is what you do. So what we did is we introduced the linear actuators, we rebuilt the system again, and then we simply anchored by a weight acting onto this with 2 newtons to make sure that the material would respond as we were looking for it to respond. When we simulated this, I should point out, if you look at the displacement, the error on the experimental and the simulated is in microns. There is that error there. And also, when we were also looking at the normalized stress of what was coming out of the simulation, there's also the error there as well. And because we were so early doors with this project, we put this down to the mechanical database being quite weak. And the testing really needed to actually establish more in depth about what this material would actually do under key states and conditions. So this encouraged us that we were on the right road, because we were getting results which, again, there's error there, but we were on that right road. We were confident that this material would support the body, and it gives us a bit of confidence in that. So we ran into the next test. Within the next test, all we were doing here is we wanted to look at the trunk. Again, core, lower core, whichever which way you want to see it. And what we did is we extracted these key elements, forces that were coming out, and again, basically recreated what you've presently seen, but we ran this into, if anybody's interested, we're running this on COMSOL Multiphysics. And we knew, looking at this, that there was actually losses. If you look at the standard deviation and the mean, you can see that it wasn't as stable as we'd hoped it would be. And given that the linear actuator had a conversion to moments, that had a huge loss on what we were looking at. When we look at the lumbar and the thorax area, one thing we were happy about is that I give them their key particular terms within the spine, so you can be aware of the particular areas that I'm looking at. What we were happy with is that when this thing was actuated, when this thing would run, it would not be too much to damage the body. Lots of present research really shows that that the body itself can withstand within 5 to 10 degrees change when it's being actuated between 2 joints. Apologies if I've not explained that one too well. So that brought us into 12. That took us into 12 months of development. So we were able to find a possible material. Now, this is the mechanics, and this is what we were looking at, just the mechanics at this point. We were happy that we were exceeding, in some cases, we were competing where metal components were there, and we were happy that this had a lot more potential than what we'd originally thought it actually did. One thing that we were also pleased about is that it had the possibility to allow for accessibility and ease of maintenance. The idea with this system is that it would slide on and off each joint within this system. We could replace it, so we could essentially grow that spine, or we could minimize the level of joints on it to actually make the spine smaller. One thing that we really did get super excited about is it wasn't just children it would support. We'd started to realize that some of the results that we were getting, again, we still needed to do a lot more testing as of yet, but we'd realized that this type of material had the potential to support more adults, more of a larger mass person. And this was extremely exciting, because what we were starting to see is a possibility. I need to stress this is just a possibility, but we were starting to see a possibility that we could, in essence, offer this to a lot of others. We were in a position where what we could essentially do is offer this to anybody who is struggling with mobility, or for small SME companies. If you're thinking of someone, say for example, who works at the local supermarket, who's holding a box and is having to lift upwards, we could offer this type of technology. Again, but this is the type of things that we were starting to think about. However, there's lots of holes in this work. We were aware of this, we knew this, but we needed to answer, could this be done? And we were really positive about this, but we were moving very slowly. I should point out, this took us just over 12 months to actually get this far. And this was just 2 of us at the time. This became an interesting area, the study of antimicrobial resistant polylactic acid. This is what we concluded with. In fact, I should point out this slide is one thing that we presented within our team originally to actually say this is where we need to be looking, because polylactic acid in itself has its own issues. The mechanical material test data, when we actually looked at some of this data, it was bits, it was scattered, and it was very much inconsistent, not inconsistent. There were some great publications out there, but we wanted to really specifically test this around the assistive technologies more than anything else. And we wanted to also look at the redesign of the system. Now, I'm sure some of you in the audience already are probably sitting there thinking, that has so much resistive area, and it genuinely did. One thing we've realized once we put this together, because please forgive us, this was our first step that we were making. One thing that we'd really noticed with this is if you went to sit up, and then let's say we went to twist our core, that twisting of the core would be next to impossible to achieve. So we'd realized and we'd learned. So the reason that this first iteration is quite personal to me is because we'd learned so much, and so much had come from this. So phase 2. Now, I'd like to, I'm going to tap into Sean in a few moments, if you don't mind, just because this is where we'd trickled along and we made some small steps, and we were very proud of these steps that we've made. Some of the most biggest things that we started to realize is there was so much to learn. There was massive levels of things to learn from this. And then I was introduced to Tinius Olsen. Once I'd met Tinius Olsen, some of the guys there were so helpful, and they've been extremely supportive. They've lent us one of their 50ST machines for us to start looking at this a little bit more. But at that time, I also met Sean. And I must say now, and it may come, yeah, I must say now that from Sean's input, we have not, and Sean and Tinius Olsen's input, we've not been able to move in such a quick pace before. Through Sean, I was able to become involved with ASTM, and I'm now one of the executive committee members with ASTM. But what this did is, rather than this being a small academic project where we sit in a corner and we make small steps day by day, it allowed us to get out and start communicating and talking about some of the work that we've been doing, and also sharing ideas. Some of the ideas that have come from interactions with Sean and also with ASTM has proven extremely excellent. So from the 50ST, what we'd now been able to start really looking at is the mechanical test data. So this is presently up to date what we have been doing. Now, I have been using a material which is an antimicrobial copper material. Some of you may have come across this before, and we are looking at the material test data. Now, I've been interfacing with that company, and we've been just talking about that material. What we're also interested in, and this is where Sean's input is going to get tapped left, right, and centre, is about the test data of the antimicrobial material after corrosion. Now, some research out there at the moment does suggest that polylactic acid against the human skin can build in microbes. These microbes can have a surface residual effect. And what we're keen to know about is, does it affect the overall geometric structure? And also, how antimicrobially efficient is this material? What's the cleaning regime? There is an awful lot to be considered in what would be simply seen as a composite material or a specific 3D printing material. There's a huge area that really needs to be considered within this. And obviously, as ever, to make sure that I don't compromise on key data, we've been following the ASTM D638 on plastics and looking at dog bones. And obviously, I've been asking with Sean and just dealing with and chatting with Sean about this as well, because we do want to make sure that any type of data that we're producing is a good mechanical data, because we don't want to simply just say, yes, it works, when there is problematic issues from the start. The post-microbial corrosive effect, this is going to be our next study into this key data. And again, this is probably something that I'm going to meet up with Sean with about this. Sorry to surprise you, Sean.
I think this is a good point, if you don't mind, Matt, to kind of dovetail into some of the questions that are popping up.
Yeah, absolutely.
You know, when you do finite element analysis, these are all based off mathematical computations, and so they're hypothetical. And even though they can be proven out, what we do know is that through material testing, through having a testing platform, we're actually putting this forward and coming up with solid data to support our FEA. And that's fine and grand if you were the only folks that were looking at this. But we know that there are other suits out there. A gentleman, and I'll address Stephen, said there's already a commercial available exosuit, and that's true. There's more than one. However, it's our responsibility in society, not just in ASTM, but in academic society and the testing platforms, is to provide a level playing field and feedback that information. And we do that through ASTM and through the testing platforms and through the educational facilities. So the good news is that we have a meeting place where we can all get together and find out what we need to do to make things standardized, and so that we don't spin down a pathway that has already been spun down previously. We're not reinventing the wheel. So the beauty of what's happening with Matt and his team, and with the interjection of Tinius Olsen with the folks at UCLan, and also our overall exposure at ASTM, is that we can share ideas. We can talk about the negative effects of the acid, and we can talk about the positive ways to approach it. But what we want to do is ensure that we're trying to make our society safer, more productive, and healthier. And that's really what we're trying to do. At the end of all the things that we try to achieve at Tinius Olsen by putting testing platforms in different facilities, in different testing areas, is to ensure that everybody is testing the material or the product so that it's safe and capable to be used in a safe and efficient manner. And that's most important to us as a society. So the beauty of having a application at an academic facility is that Tinius Olsen can gather some information. So it's a win-win. And it is a bit selfish for both of us, because we want to be able to springboard off of this to come up with, if you think about it for loss of a better term, a better widget or a new platform that is accessible to all the folks at every economic point in life. And I'm extremely impressed by your approach, and I'm extremely impressed by how fast things have ramped up, even during this very tumultuous time during this pandemic. And it's a testament to your tenacity and your drive. So I've enjoyed this, and I think it's been lovely. And if anybody else has any other questions as we move forward, I'm going to pivot off that. I thought this was a good interjection point to talk about how we had our relationship and it's really going forward. So thanks for that few moments, and I look forward to working with you forward. And I'll pass it back over to you, Matt.
Yeah, thanks, Sean. Yeah, I'd like to just pull up behind that one as well. The fact that there is already commercial exoskeletons out there. You're absolutely right, and this is not to try and trump that system at all. This is to really look at the idea of accessibility. So if this is something that is on the platform at home, if this is something that families need to be able to get access to, we want to be able to do that. And don't get me wrong, I know these are grand plans and real hopes and dreams, but it's really about helping as much as humanly possible. Right, so in this key stage of where we are now, onto the materials, I alluded to that we'd already learned from our mistakes. The exoskeleton system that we've presently got didn't do like we'd wanted to. And what I'm about to show you is our new prototype. And this is a CAD render. I can't discuss too much about the actuator system because this is quite novel, and we're hoping that it has a lot of potential with it. But let me introduce this. So this is a more a better approach to what we've been doing. This is the present system that we've been looking at. And unlike our last design, we've been taking a lot more steady steps with this. What you'll notice with this is that the spinal structure still remains. Now, the idea with this is that if you are to lean with this process, what we'd actually get is passive elements. So as you lean back, part of that structure will actually capture some of that force, and we're attempting to anchor this down to the ground. And one thing that's been really great for us to really appreciate with this, or realize with this, is our actuator method. We think that a new approach towards the actuator system is to not think about the exosuit or the exoskeleton, which, to be fair, I've not defined clearly as from the start. The exosuit will attempt to mimic the muscular contraction. The exoskeleton will attempt to act as a large base structure, which can be often passive or driven So you can end up with a part that is actuated and the other side which is passive. So I know Ford have an amazing exoskeleton out at the moment, which is entirely passive with some sensors on board. It's phenomenal. What we think is a combination of the two, part suit and part skeletal structure. Now, provisionally, some of the things that we've noted is by using this type of approach, what it can actually do is it could act as a contraction. What it could actually do is it could act as it could act around it, and also it could almost imitate our spine and also imitate our muscular contraction. So, apologies. This is our first study piece. This is designed around anchoring to the foot. We've done some provisional FEA. Again, this is just to look at the FEA. And we are now in a position where we are going to start looking at what is nicknamed drop foot. We're going to be looking at using this approach, using this system to try and allow to assist the lifting of the foot and the lowering of the foot as somebody is walking. And again, this is our first running human test, and we are quite excited about this because, again, we started off with the large inaccurate structure, and we now think that we're starting to refine to start look a little bit more at how these systems should genuinely start to look. I'd like to just acknowledge some of the key collaborators. Obviously, Sean, you're on there. Obviously, Sean's Tinius Olsen and the Astm, so you can often be unsure who to write on there. Some of the guys I've been working with at Ultimaker, and some of our professors at the university have been phenomenal in their support and their encouragement in taking this team further. I'd like to introduce you to the team, and there is a key thing that I didn't explain, and I'm quite proud of this. So first things first, the team at present who I've been working with, Jorge is our antimicrobial expert, and he has been doing lots of testing, looking at the effects of microbes actually on polylactic acid. He's been working with us really closely. In fact, again, I'm from mechanical engineering predominantly, so I've been learning crazy amounts on the cultivation of microbes and their ability to exceed and so forth. I've learned so much. When I'd alluded to the originally that there was two of us sat behind a desk looking at this, Edward Sanderson, he was formerly one of my students, and we just took it upon ourselves to try and see if we could look at this further. And both Stephen and Matt, they are both good friends, and we are just at the moment just looking at strategically moving this forwards. Finally, I do have one team member, is Christina Marshall. One thing I didn't tell you about is I've actually asked Christina this to make sure that I'm allowed to introduce her. Around just a little over a year ago, well, just a couple of months before the project started, there is an outreach project here. For those of you guys in the States, this is more of a K-12 approach outreach. And Christina entered a competition. She drew on a bit of paper about why is there not a special shirt out there that can help children be mobile. And you know, when you sit there and you think there must be millions of these in the world, and yeah, this is very much something. And the truth of it is children grow. So if you spend an awful lot of money developing a skeleton for a particular age range, most of the time, by the time they've got to it, they've grown out of it. One of the key things that we'd realized is that she was onto something special. Obviously, in her competition entry, when we'd reviewed it, this system didn't exist. but the idea of what she proposed was phenomenal. And since then, since this has been moving in such a direction, I still remain in contact with Christina and her family. Christina since then has now become, for anybody who's in the UK, Christina has now become an honorary, she's been given a scholarship to go into rehabilitation nursing. And I hear from a family that she's doing extremely well at the moment. So I don't like to not give acknowledgement where commendable things have occurred. So yes, that's the team. So in summary, thinking about the aging population, there isn't just one solution. Not one thing will solve all this issue. Thinking about supporting of children, again, there isn't just one solution. But the way that I like to think of this, and I'm sure you'll join me in this thought, Sean, that the way that I like to think of this is that this is an inspirational point from simply Christina's idea of, does this exist? For us following this through, somebody we're encouraged that with this type of technology, we can inspire and hopefully we can change people's lives. I think with the design cycle, when we're actually considering the design cycle for applying this types of technology, and not just exoskeleton technologies, we do need to think about the actual, what it's being designed for. So the user really needs to drive this cycle. So what I would say, and I was just as guilty when I first got into this system, I came at this with a mechanical engineering approach. And only from getting out and interfacing with Sean, people at Astm, and with colleagues who are actually in the healthcare, it really inspired us, it gave us a way of thinking, and it helped us move forward. So it just instantly told us that this can't be something where somebody sits in a carriage or anywhere like that to simply come up with something that is straightforward. Technology is great. And I am an avid lover of technology, always will be a lover of technology, but it needs to be affordable. It needs to be accessible. We need to be able to offer this to as many people who need this assistance. I personally still now, and when I first started on this project, believe that the only real answer to be able to do this is with composite materials, or with new and developing materials, but at the same time not compromising on testing. Hence why my interface with Tinius Olsen, with Sean, and with Astm always keeps it that if we're going to develop this, it must be safe, it must be accessible, and it must be not something that's crazily complicated, or else we've defeated what we wanted to do. And 3D printed materials, at the moment, we've seen they do offer an insight. They're offering an adequate solution to supporting key areas of the body. Granted, our skeleton will need further development. Any structure will always need development. As my lecturer once said to me, any great project is never really finished. And I don't think this one will be, because it will always leave room for improvement. And just as a side note from this, one thing that we've realized is that with this type of technology, we could start to look at supporting of astronauts. And granted, it wouldn't be polylactic acid. We'd be having to look at a different material. But one thing that we'd realized is with our new way, when an astronaut is in zero-G positions, these systems are often assistive. But what if they're resistive? What if when the arm moves, what if the system itself is no longer helping you, but it's resisting your motion? What we'd be doing is tricking that muscle to fire. And again, I know that's a huge area, but it's just to throw that thought, food for thought out there. Other than that, thank you so much for listening, and I'll pass it to you, Sean.
Well, thank you, Matt. I appreciate that. There's a lot of information here, and to the audience, I would challenge you to think about what's on the horizon. What can we do collectively as academics, professors, engineers, users, from any aspect of society. It's our responsibility as human beings to try to do things better, to be more right, to have a platform where you feel good about what you're doing and you're contributing to society. We don't have all the answers. We probably, with your help and with some feedback, we'll be able to find those. We can work together to make our society a better place. What I would always ask people to is remember this: it's our friends and our family that need the testing and the academic viewpoints of all our colleagues throughout the world. And because of that, we're able to look to the horizon and beyond, as Matt alluded to, into space. It's important for us to also understand that we do this because it's the right thing to do. Our family rides in planes, our family goes over bridges, and our friends are taking different vacations, and we want to make sure that thing is safe. So, as I stated before, it's an interesting and exciting new avenue that the world is going down, and this specific assisted platform that different folks other than Matt are working on are exposed only through development of testing, academic, and ASTM and ISO and other standard developments. And that's what really opens our eyes to the connectivity of the world. I think that through different platforms, we'll find ourselves further along the next time we have a conversation. And I think with that, we'll start opening up with some questions, and we'll just take it from there. Go ahead, Chelsea.
That's great. Thank you both. And just to add, we've had some comments already from Kevin and Sohail just saying what a fantastic presentation that was, and some really insightful information there for advances in medical technology. So thank you again. It was really an interesting presentation. So to kick off, we've got quite a few questions. So just one we received prior to the event. So this was, what description best matches your exoskeleton project? Assistant for the non-abled body community, children or adults, enhanced mobility and ease of use for manufacturing assistants, a precursor to fully functional autonomous robotic assistants, or all of the above?
It's a great question. I would say it is really attempting to answer all of the above. I'd say answer, but be a precursor towards all of the above. But yeah, it's a great question. That's
great. And then another popular question we've had from Sohail Norman is, did you use any other test methods apart from ASTM D638?
Oh, it's a great question. Yeah, at the moment, no, we've been looking at the D638 and we've been using the whole range of different ASTM testing methods. But at the moment, our focus is just with the D38, D6. Oh, I've got myself confused then. But yeah, our focus has just been looking purely around that particular test method. And it's just because what we really wanted to do is look at that particular data set that we were getting, because I think Sean answered this great really when it came to the FEA. FEA is great, you know, and these are all theoretical. They're always theoretical. But what we wanted to do is to make small but solid steps. So our test method, we wanted to make sure our test method was accurate and was a good representation, and then using that data to feed back to our numerical models. And then once we set up this solid data set, then we can start alluding further. But it's a great question.
Yeah, and I'm going to jump in a little bit there, Chelsea, for just a moment. When someone asks if our test is done to not just ASTM, please keep in mind that most of the standards are married in one way or another. The standards that are based out of America, out of North America, which is based on ASTM, are hand in hand with the ISO standards, the International Standard Organization that is throughout Europe and the UK and the rest of the world. We have liaisons between the two organizations, and we're all under the same premise, providing a testing platform, a standardization across the world. so that we all get the feedback and get the advancements in the nuances of all different testing platforms. The testing platform that Matt and his team are using now is predicated on testing platforms that have literally been around for hundreds of years. And those were actually prior to the advent of this type of advanced material. That testing was done on metal. And they just kind of springboarded off that and modified the testing procedures to be utilized with composite materials or hybrid materials, if you will. But that's a great question. I really like that question, of course.
Yeah, and we've got another question here from Ashish Sharma, and it kind of alludes to testing processes. So what are the various analytical and clinical tests that you perform to assess the exoskeleton's performance and establish proof of concept?
Right. Okay. So obviously with a direct clinical approach at the moment, we've not been able to test on humans. We wanted to be sure. Our first real step at this point was to establish that it could even support this level of force that was being activated, that was being applied to it. This is why we stayed away from attaching to anybody as of yet. Moving forwards with it, we do have a key, it's slipped my mind to be honest. We do have a key clinical series of testing that we're going to do, but I'm always open to responding to that a little bit further offline. So if anybody does want a little bit more detail and a lot more data about what our test procedures are going to be from the clinical side, please do email me.
That's great, thank you. And we've got an interesting question here from Mike James, who asks, what is the expected lifetime of the exoskeleton based on failure modes? i.e. what are the implications for material selection? He's wondering if some other material might give a device that would last longer.
This is great. I was, you know, when you hope that the question is going to appear, and yes, this is the one. This is absolutely. So the reason I'm so excited about this topic, and the reason I get so excited with talking to this topic to Astm and Sean, is purely because he's right. The truth of it is the reason that we looked at PLA is it's the most accessible material to all families, to all. I mean, I think one of the biggest selling 3D printers in the world is the FDM 3D printer, the desktop 3D printer. But yes, he's right. What we'd realized is that if we looked at alternate materials, we could gauge to a different life cycle process. Because again, the trouble is with PLA is its fatigue life is relatively short. We could be looking at 1 year to 2 years in a great condition for PLA. But and in worst case scenario, we could be looking at months. But what was important to us is that each component values roughly UK price of around £1, and that's what we were most interested for. So, but yes, it's a fantastic question.
Thanks for that. And we've also got a question from Ram Singh. He asks, is there any possibility to monitor and verify the predictions and measurement data post-installation of these components after installation in the patient's body?
Oh yeah, I should spell out. This is not invasive. This is non-invasive. So this would be worn as best way I could describe. Think of a rucksack. You put on your rucksack and you can clip it on here. This would be worn as an assistive tool towards it. But I would like to answer a little bit more of that though, if you don't mind. I'm going to try and keep it short. The strain gauges, we have started looking at printing strain gauges into it, just so we can look at the deflection of this running. But again, this is something that I've started to allude to with Sean. Yes, sorry, Sean.
Well, you know, it's funny you bring up strain gauges, because we're also having an interaction with another UK company that we're going to utilize virtual strain gauges, and that we're going to utilize what's known as an optical extensometer that we can reposition the strain gauges in any number of fashions, and they never come off the material because they're implied through virtual operations, and it's going to be brilliant. And that's one of the ways that we're going to expand the testing, that's for sure. So I just wanted to throw that in there. That would be coming up in the very near future. So
Yeah, and we've got another question here, and it's asking if you're considering the corrosion, have you also considered the blood-based corrosions and the impact of composites on allergies?
Well, I keep saying fantastic question, but again, another great question. So again, I'll spell out, my pure background is mechanical. So if Jorge is in this audience, I do apologize if I'm butchering his topics. But yes, we are clear that the level of bacteria that sits on the human skin is a massive thing that needs to be considered with work with Jorge and our company, the Copper Company, and also with getting advice from some of the guys at Astm. What we're actually doing is we're trying to look at the possibilities of all these different things occurring. So if there is a cut on the body, how do we address that? Is the material going to act badly against them? Because yes, the point is yes, it will. So how do we start to address that? What type of coating should we really be looking at? Is it a spray coating, or what's the maintenance? So yeah, it is. And I do appreciate in my slide, I give this 2 titles, but really it's a huge area by itself. And that's why it's grown to such a degree.
I can see Sean was typing an answer to this question, but I'll raise it live. But I suppose whilst we're on the subject of kind of allergies, that kind of thing, but there's a question here from Stephanie Ward just asking, will you get to the stage as to how comfortable it may be?
You want to take that one, Matt, or can I delve into that for just a moment?
Yeah, you delve into that, Sean.
Okay, so one of the beauties of having roundtables from an academic standpoint in a testing platform is we can compare all that data. It's called interlaboratory or intralaboratory studies. And with the data that we'll collect, it's going to be what is the wearability factor. And because we do a lot of testing for other avenues of clothing and apparatus, helmets, etc., that's part of the portion of it, right? We want to make sure that it's comfortable. I think as we move forward with some of the other analysis that we do through testing, and then I'll spring it back over to Matt, that will be a part of it. But the good news is, since this is a modular system, we want to keep it as comfortable as possible, and we'll know the feedback from the end user. Hey, I think I'm outgrowing it. Let me go to the next step. And that's, I think, is the big picture. And but with all the feedback from different testing platforms, different feedback from the standards development, we'll get that information, not just from Matt and his team, but from all the other teams worldwide. That's why I think this is such an exciting platform.
That's great, and we've got a few questions now just based on materials. Faze Ahmed has asked, PET and carbon is compounded materials. Would they be available commercially, or are they developed in the laboratory?
This was actually commercial. This was purchased directly off the shelf, and what we've done is we just pulled what mechanical data sheets were presently on it, and we've gone in feet first a little bit, because we didn't want to just end up, I hate saying this because I'm sure a lot of people will shoot me for saying it, but we didn't want to just make another simulation model. We wanted to start bringing this to life a little bit, and then making steps backwards to make sure we've done the right thing. But we learned so much from this. Yes, the answer is yes. It was off the shelf.
Great, and we've got a similar question, whilst on the subject of PET, Deborah Ward asks, what form is the carbon in within the PET?
Is this referring to the manufacturing process behind it? The carbon fiber is in nanoparticles, is the best way I could answer, but I don't know if that answers that question correctly.
Yeah, Deborah, please feel free to jump in another question if that hasn't asked your initial question there. We've also got another really interesting question from Ashish again, which asks, most of the commercially available exosuits have a major limitation of limited power supply, which limits the time of usage of exosuits to a few hours. He asks, what are the possible solutions? Does replacing material used with non-metal composites reduce overall power consumption?
Oh, he's getting me in an awkward spot now. Right. So our new actuator system, because we're looking at less of the huge mechanical type approach, because we're looking at the suit method of where we're drawing at the point of contraction. What we think, and I like to say what we think is we have a drop in power that's needed. So we've dropped the need for that level of force being there, because he's right. We've been able to drop weight of the actual material. And I'd like to say it was focused purely around the weight aspect, but it really wasn't. Our real approach was that we were targeting children, and we're still looking at children. And the truth of it is this system needed to be light, regardless of what the power consumption was going to be. But yeah, on a knock-on approach of that, we've been able to actually minimize that level of power usage that's out there at the moment.
Great. And actually, a question from myself really is, what was the initial inspiration, or is there a backstory behind what kind of ignited this project to begin?
I'm a firm believer in public engagement. I've always been a firm believer in public engagement. I myself, I'm dyslexic, so in school, if anybody in the audience is of the same, you'll know that in school at your age, it probably wasn't the best experience that you'd had. Now, I firmly believe that children should, if they have a good idea, they can be any age. It's a good idea, regardless. And meeting this young lady, Christina, when we first met her on this competition, when I met her originally, she was convinced the exact same thing. She could never be anything special. And I sat down with her and I said, Christina, this is something special. I don't know for sure, but I think this is something special. And when I'd looked at this further, and I looked at what she'd entered into this competition, I thought, this is incredible. This can absolutely change people's lives. And if it doesn't change someone's life, it's going to inspire somebody who will follow up on the footsteps that we're making. So the second that you realize you're making these level of changes and you've got the possibility to make these changes, who couldn't stop themselves?
No, that is really interesting. It's quite exciting to think, you know, imagination and where that can lead to an idea that could potentially help, you know, a lot of people. So we've got another question here. So what do you feel would make the system you're developing different to what, you know, is out there already? I think we did allude to this in an earlier question regarding other exoskeleton suits already available, but what do you feel makes your project kind of stand out?
Oh, this is where I drag everybody in from this. With the guidance with Theo and Sean, with looking at ASTM and making sure what we're producing is safe, is usable, and recreatable dead easily. And also, it works. We're being able to offer this for people. We'd be able to offer this to healthcare systems, so be it stateside or in the UK for the NHS. We can give this for people who can actually, again, it can change people's lives with that. Because we are now moved towards this hybrid approach, you don't have to have it with an electronics actuated system on it. You can just use the mechanical side to minimize that force for the workforce. And the one thing that makes it different for us is that it's cost. Our focus is about the accessibility. It's about everybody gets a piece of this. I know you'll probably be too young for this, Chelsea, and some of the audience will know this, but I'm a Tomorrow's World child. And Tomorrow's World was a TV show when I was a child, and they always had this new technology, and it was always big and exciting. And then you often sit back, well, that's amazing. I'm never going to be able to afford that. But what if new technologies you were able to afford and you could have access to it? So that, for me, is what makes this different. I'm not targeting millions of pounds. I'm actually targeting next to none. And that's where our personal approach is.
No, definitely. I've not watched that program, I'm afraid. No, you may have also, I think this could be, you've probably answered this in the previous question, your response, but why did you not consider using conventional manufacturing methods? By using 3D printing, what extra does it really offer to your project?
Yeah, I mean, I was actually asked this a few months ago by someone from a healthcare. They said, well, on large bulk manufacturing, if we have the molds, technically it is cheaper, which is correct. But what you do is you offer families to be able to deliver healthcare at home, in lack of better words. You've got, say you've got mum or you've got dad, they're low income, but say they've got a child that suffers with mobility. What you enable them is the accessibility to help that child that little bit more. But yes, it's a great question, because some of the conventional methods on large bulk will actually be technically cheaper. But that's what I think this offers.
No, that's really interesting. We have answered the majority of questions we've had in from delegates. So, but if there are any other questions you've been kind of holding back on, delegates, please feel free to just use that Q&A. We've got a bit of time left. So whilst we're waiting for any kind of final questions to come in, Matthew, Sean, is there any kind of additional comments? Where can people find out more about what you're doing, and other avenues to get involved, I suppose?
Well, I just want to jump in here and say a couple different things. As Matt alluded to, technology is ever dynamic. And as we move forward, I'm going to disagree with Matt, because I like to do that. And the reason I'm going to disagree with him is that as our technology moves forward, specifically with hybrid and 3D material, the cost will drive down because technology is increasing. And as we continue to move into the area of producing, heck, today they're producing 3D homes. 3D homes. And so what we do know is that with this exciting technology and through all the testing platforms and the societies of standards and the academic societies, there's a lot of exciting stuff out there. And the more that we can get it into the mainstream, which is really what standard development is about, is that everybody can see the same thing, that will drive the cost down, and it will make it more accessible to those that are on an economic handcuff. And it's important to also note that that's really what it's about. It's trying to put technology in the use of folks that need it most, the folks that are not able-bodied, the folks that have less economic power than the rest of us. Because we do know that, as Matt mentioned, there's financial entitlement, and everyone's like, of course we can afford that. But that's not the truth, is it? What we do know is that we want to make it accessible no matter where it's at in the country or in the world, right? I don't care if it's in Asia. I don't care if it's in different parts of Asia, in India or China, or in different parts of Europe and Eastern Europe. We have to make products, no matter what they are, accessible to all of society and all walks, no matter what your economic platform is. And that is really what this is all about. I'm excited from a testing platform, and that's selfish. But it also, I know through our interactions with the societies of standards, through the testing platforms at Tinius Olsen, we can provide a testing platform, because if you don't know how to test it, we can work together to find a platform that works for you. And that's really what it's about. It's the collaboration and the partnership between the testing company and the end user, or the development organization such as Matt's.
That's good. Yeah, completely agree. And I think in a year we've had, I think all the delegates probably agree just how important communication and collaboration really is, and has been highlighted in the past 18 months. We've got one, I think, final question here, again from Faze Ahmed, who just asked, regarding the compatibility of PET carbon, are you planning to use coating on the surface, and how is the possibility of leaching of any toxic ion to the human body?
So that's heavily loaded is the question. So when it comes to PET, what we've actually started to do is actually move slightly away from PET. Now, I need to, what I mean by loaded is there's a lot more in that. So what we're actually now doing is we're using dual head printing. One thing that we realized is that one thing with technology now, dual headed printing is a big accessible aspect. So we can have the hardcore material within inside of a centralized point of that component, but the outside can be our our antimicrobial material, which could be TPU, which could be PLA. And again, these are the two materials that we've been looking at the outside skin. But again, we can't confirm that it will be that as of yet, just because we still need to do a lot more testing yet.
Oh, and I'm just going to fly in another question we've quickly received because we have got a little bit of time. Tom's has asked, you mentioned about the growth of the body aspect. How has that been taken into account, he asks, as in typically how long could a particular size of this exosuit fit comfortably for a person?
Our first design, now for anybody who's mechanical, you'll know this is a continuum design where the system locks together. In fact, what's behind. The idea is that these systems, you could simply slip on and slip off. You could slip more of these joints onto position. Now, the reason I'm alluding to this is I can give you an age range that we'd originally looked at with this one in particular. We'd started off looking at 8 years old, and then we'd moved to 13 years old. And we were confident that our overall structure and design, based on growth on the 90th percentile, we knew that we could keep sliding these joints on, and it would allow for that. But again, nobody's black and white. Not everybody grows exactly the same. But once we get to around 12, 13, this would need updates. This would need slight changes towards it. But that's what we've been targeting at the moment.
No, that's great. I think that's all our questions, and we're getting some fantastic feedback from delegates. So we're very pleased to hear you've enjoyed the webinar. And yeah, there's some, oh, we've got another interesting question. Sorry, Matthew, I'm keeping you on edge here. We've got a delegate who asks, if you're using a filament-based printing, the debinding process may take a long time compared to regular 3D printing techniques. So what debinding process do you use? How do you prefer to support the body while increasing the Z-axis gaps?
Yeah, between the Z-axis positions. Now, I've just thought, one thing I didn't spell out is we are not targeting paraplegic with this design. This is purely more assistive. And so for supporting the Z-axis of the debinding aspects, yeah, it's caught me off as that one. It's just because what we've been really looking at the moment is from our testing with our conventional dog bones, is we're not sure about exactly what that debinding element is, or the interboundary layering between it, if I'm receiving the question correctly. So what we're trying to do at the moment is we're running a lot of the D638 tests to allow us to understand that a little bit more. And I know that there's present data out there at the moment. I do know that there's present data out there at the moment, but we're doing this because we found a little bit of inconsistencies in some of that data. So we're trying to just bring it home a little bit. So at the moment, that's where we are, I should say. Oh, sorry, Sean, keep cutting you off.
No, you're not. But I just want to kind of address that as well. It's a great question. And as we step into the next phase, and as this project moves forward, year 2, year 3, year 4, those will be applications that we will address, I would assume, from your viewpoint. But from a testing platform, that's why we want to approach it from a video extensometry platform, either DIC, which is digital image correlation, so that we can look at all those different axes and the different interactions in the factors of stress and strain. That's a great question. It was a question I had for you a while ago. So I love that. This has been a great webinar. I've really enjoyed this.
No, yes, completely agree.
And Chelsea, are you going to the attendees? You will forward mine and Matthew's contact information. Yeah.
Yes, I was just gonna wrap up actually and say, you know, if you are interested, want to find out more, Matthew and Sean's contact details will be included on the follow-up. So please do feel to reach out. And yeah, thank you for attending today. We've had a really engaged audience and there's been some fantastic questions. Matthew, it'll be great to see, you know, how this develops and the collaboration with Tinius Olsen. So yeah, it would be great to invite you back and to see how, you know, the testing is progressing.
Don't invite me back next week because you won't get much development.
Yeah. We do look forward to it. And just to let everybody out there in the audience know, Matthew and I plan on working collaboratively probably towards the end of July or into August as your restrictions lift, and then setting up a number of different test platforms. And we very much plan with the help of IOM3, iCapture, our own marketing folks, to get another webinar out there. So everyone, keep your eyes open, pay attention to what Chelsea says, and we really look forward to seeing everybody soon. Yeah,
absolutely.
That's great. Yeah, so I'll wrap up. So thank you for everyone who's still with us. For those who have had to dash off, any colleagues who may have, we are recording the webinar and that will be shared as soon as possible. So yeah, thank you once again for all your questions, and to find out more about what future Inform webinars we've got planned, keep an eye on the IOM3 website. So thank you, Sean. Thank you, Matt. I hope, Sean, you have a good rest of day over in the States there. And Matthew, who's in the UK, I hope you do manage to get out and make the most of the heat wave we're experiencing today.
So brilliant. Thank you, Chelsea, for the support and facilitating this. It's been lovely.
That's great. Speak to you all soon. Thank you.
Right. Cheers. Talk to you soon. Bye. Matt, I'll talk to you real soon.
Yeah. Yeah, definitely.
All right, bye.